All right. So here we are. We're talking about thin films again. These thin films have kind of been drawn so that we can do a bunch of little iterations. Say like, oh, what if this is this way, and what if this is that way, and what if we changed it this way? So let's go through that. Okay. I've got three materials, and I'm just calling them material one, material two, and material three. But if I wanted to be like real specific, let's just say that the top material is air, and light's traveling from air. That seems reasonable. And it's hitting a film of soap. Maybe I'll zoom in on that to make that nice and big because I'm going to contain all my thinking within this box anyway. Okay, air, soap, and just to be weird, let's let the bottom one be argon gas. Can't think of why we would do this, but sure. There's a soap film floating above argon gas, or maybe this is a bubble that's been blown with argon gas, as opposed to like just breathing. Anyway, air, soap, argon gas. And so the indices of refraction would be 1.00 for air. It's about the same as a vacuum. Index of refraction for soap, and I know it's going to depend on the brand, but let's just say it's 1.50. By the way, I would give you the index of refraction for material for homework. It would be in the textbook. It would be a table of values. Okay, so don't try to memorize the index of refraction for soap or something like that. Okay, index of refraction for argon is 1.10. That's not brand dependent because argon is what it is. And what we said earlier was that when light reflects off of an interface where the reflective surface, as opposed to the incident surface, where the reflective surface is a higher index of refraction, what does the light wave do? It inverts, yeah. So I'm going to make a little label there. Notice that material 2, soap, has a higher index of refraction than material 1. So I'm going to label right there inversion at the upper interface. Notice that there isn't an inversion at the lower interface because N3 is 1.10 and N2 is 1.50. So that's a lower index relationship between the incident material and the reflected material. Okay, so no inversion at the lower interface. And so I'm just going to make a note. Oh, maybe I should say there, since, that's what the upside down therefore statement or symbol means, since N2 is greater than N1. And I'm going to make the statement, this scenario has an odd number of inversions. Due to surface reflection. It's just an observation. I'll underline the word odd. Then I want to look at the one just to the right. And as people are finishing writing down the words in red there, let's add in some information in the one to the right. For this situation, material 1, let's keep it as air, 1.00 for the index of refraction. By the way, notice that index of refraction is unitless, which makes sense if you go back to the equation. Vn is equal to C over N. Yep. Yeah, I'm going to move it over. Just I was waiting for people to finish writing. Can I move it over, guys? Yeah? Okay. All right. So index of refraction 1 is going to be 1. Index of refraction 2 is going to be 1.5 again. And so it looks like we're probably still dealing with air and soap. But the third material, I'd like it to be glass. And again, it depends on what the impurities are in the glass, but crown glass is considered to be about 1.70. Okay? So 1.70 for our glass. And when I look at this, let's look at the index of refraction relationships. It looks to me, again, because we haven't changed the first two materials, looks to me like N2 is still greater than N1. But then when you look at N3 versus N2, can you see the inequality there? Right? So N3 is greater than N2. And so We could label these guys up. We can say 2 inversions occur, one at each interface. Okay. And if there's 2 inversions that occur, I mean, I guess it seems obvious, but we can make the similar statement. This scenario has an even number of inversions due to surface reflection. Okay, just an observation. Higher indices of refraction for the reflected material as opposed to the incident material cause wave inversions, like a fixed-ended string. Okay, and I want to scan downwards, leaving a little bit on the screen there for people that are slow writers. Let's take a look at this third quadrant here. We've got, all right, well, let's let N1 be 1.70. So we're going to move glass to the top this time. We'll let N2 be 1.5. Oops. Oh, man. Put a white out there. It didn't fit my decimal place in. 1.50. So that's still soap. And we'll put air on the bottom this time. 1.00. So glass, soap, and air. Now, the fact that it's glass, soap, and air, and I look those values up is irrelevant. That's fine, okay? Could just be material 1, 2, 3. But as I look at this, let's take a look at the number of inversions. Is there an inversion at the upper interface right here? What do we say? No. Is there an inversion at the lower interface? No. Oh, okay. So I would say, I could make a statement like this. I could say, well, N1 is greater than N2. I could say N2 is greater than N3. No inversions. Oopsie, no inversions occur. Okay. Now, this is one of those things that the philosophers can deal with later. But do you suppose that 0 inversions counts as an odd number or an even number? Yeah, 0 counts as an even number because it's not odd. That's all, okay? So this has 0 inversions. Which is considered even. And whether or not everybody considers 0 to be even or not, again, I'll leave that to the math philosophers. But for us, it's even, okay, because it's not odd. And I want to slide sideways again. So this has 0 inversions, which is considered an even number. Back over this way. One more permutation, and then we'll sort of build our equation set conclusions, okay? So for this one, N1 is 1.70, N2 is 1.00, and N3 is also 1.70. Again, this actually is the first example that we did in the previous part of the note where we have glass, we have air, and we have glass again. So this is air wedged between 2 sheets of glass. This is actually what we did, a few minutes ago. Okay, but as we look at this, where is the inversion going to happen? At the upper interface of the air or the lower interface of the air? What do you say? Lower. Yeah, look at this. N3 is greater than N2. Inversion occurs at the lower interface of the air. And I'm going to say only, because as I look at the transition from N1 to N2, surface 1 to surface 2, there's not going to be an inversion there because N2 is less than N1. So then we can make, again, this statement, this scenario has an odd number of inversions. Now, these four scenarios, it seems like it's kind of repetitive, and I get that sometimes repetition can be annoying. But in the past, I've had students say, "Oh, could we just see like some examples of what you're talking about?" That's all it is. You feel like if I did more than 4 examples, it would get terribly repetitive, right? Like I know that it's a little bit repetitive. It would get really repetitive if we do more of them. But once you figure out how to identify how many inversions there are, it's not so bad, okay? So here's what I want to propose is that earlier we had 2 equations. One that I said was going to be for constructive interference and one that was going to be for destructive interference. And so if there's an odd number of inversions, I want to claim that this equation here, t is equal to 1/2 m plus 1/2 times lambda over n, where remember, lambda n is the wavelength of light in the actual film material, the sandwiched material. That equation represents constructive interference. In the specific case where there's an odd number of inversions. And we'll let t is equal to m times lambda sub n over 2 be the equation for destructive interference. In the specific case where there's an odd number of inversions. And of course, that just switches. We end up saying t is equal to m lambda n over 2, and t is equal to 1/2 m plus 1/2 lambda sub n. This ends up being the constructive equation for the thickness when there's an even number of inversions, and this ends up being the destructive for an even number of inversion scenario. And people say, well, why do they switch? Well, they switch because that odd number of inversions introduces an extra half wavelength. You see that the half wavelength is what's critical here for things being in phase or out of phase. And so if there's an odd number of inversions, then it's going to shift things off by half wavelength automatically, right? If there's an even number of inversions, then it's going to shift and then unshift, if you like. Or in the case of the 0 inversion scenario, not shift anything at all because of inversions. Cool? That's why it's a flip-flop, and that's why it depends, and that's why I said I couldn't commit earlier until we kind of like went through this thought process. Does this feel good to anybody? I know it's repetitive, but at least like, through pattern recognition, we can kind of see why it matters, right?